So I'm Preston, I'm the group lead for Group 1, and I'll be talking about the commercial air conditioning experiment. And this is a basic AHU, and what you have is, right there you have your return air coming in, and your return air is going to come in and split. You'll have a little bit leaving as exhaust air. It's going to go over an energy recovery wheel right here. And that energy recovery wheel is going to precondition your incoming outside air. Not all systems have an energy recovery wheel. They're just like kind of based on the designer, if they want to put it in or not. Your non-exhausted return air is going to then mix with your incoming outside air that was preconditioned, pass over the cooling coils. If your system has it for like hospitals and stuff, they'll have clean rooms, so they'll need UV lights to clean the air, and then they may or may not have a humidifier, and then it's just going to leave and go through the supply air to the room as 55-degree cool air. There are two ways to do efficiency for a AHU system, and you have first coil bypass factor, and that's not really used very much in the industry. And the other one is your energy efficiency rating, and that's used a lot more, and it's just your air handling unit size over the electrical energy input. And you can also get the coefficient performance from that as well, using the formula. So in design, you'll have a building, you'll section it off in zones, zone A, B, C, D, and you'll have each zone, you'll calculate the CFM rates for those zones, and you'll need to certain amount of volume airflow to cool the rooms. So the way they came up with to supply that variable amount is they use VAV boxes, which is a variable air volume box, and it runs off of a thermostat in each zone, which then controls an electric motor and opens and closes a mechanical damper inside of the VAV box. So our apparatus, you have a cooling loop, which consists of an air handling unit, and you'll have your air coming in, you'll have go over to supply air unit, supply air heater. It's going to separate the two VAV boxes and they go into each zone, zone A and zone B. Each will be separated by a wall. Each in the walls, two walls are different, so they'll have different heat transfer rates, and that's what we're going to be testing in this experiment. And in between the two walls, you'll have a hot air plenum, and that hot air plenum is supposed to model the outside air conditions as if you had that wall up against an exterior wall of a building. Those outside air conditions are 95 degrees Fahrenheit and 11 feet per second, or 7.5 miles per hour, and that's based off ASHRAE, which is the American Society of Heating and Refrigerant Engineers. And that hot air plenum is going to be maintained by our heating loop, which is just the heater, this heating supply fan, and space the hot air plenum. So our procedure is to record the dry bulb temperature, relative humidity for the lab room, record the dry bulb temperature, relative humidity, and aperture dew point for the cooling loop, run the heating loop at outside air model conditions, set the supply air temperature to 60 degrees Fahrenheit, and once the chambers reach a little bit above the set point, you're going to open the VAV boxes, and after 3 minutes we'll start recording the temperatures and CFMs for both zones for 30-second intervals over 30 minutes, so we'll have 60 values. So the heat transfer that occurs in these two zones, you'll have zone A is just the two surfaces and some sheet metal, and zone B actually has an air gap, and that air gap is going to give it almost twice as much resistance. You'll have a 2 on zone B, whereas you have like a 1 on zone A, and that almost gives you twice as much heat transfer across the one without the 1-inch air gap. So you can see that it's important in engineering and designing buildings that you have a 1-inch air gap on exterior walls at least. It'll help, you'll have a more efficient building, you won't use as much energy trying to cool it. And these are just the volume flow rates for each zone, and you can see it's almost doubled, 60 versus the 30 for the one with the 1-inch air gap. So this relates to thermodynamics by the calculations for the heat transfer across a wall and the coefficient of performance. We did those back in thermo. You know, some people, I don't remember, I had to go review, but it also relates to the real world by, in HVAC firms, they do, this like almost approximates, like almost really well approximates the selection process for air handling units and the design for HVAC systems. I actually worked at an HVAC firm last summer and did a few jobs, and I remember that in some designs you actually don't need VAV boxes. Some designs you can just have your animal unit go straight to the supply room, and then through the supply vents you can control with the little fins, little dampers, you can control how much air goes in each room without actually having a mechanical motorized damper. So that's about it. Any questions? Yeah.
So you talked about like having insulation and stuff. So you think more the insulation, like would it be more better, or like would it be less better if the insulation? If it's like, let's say 2-inch gap instead of 1-inch gap.
So if it was a 2-inch gap instead of a 1-inch gap, I don't think it would actually increase it, like from 1 to 2, it wouldn't double your resistance again, because you're not initially adding convection heat transfer in between the two walls. You're just extending the distance that the convection would happen. So it would probably only increase around like 20-30%. I'm just guessing though, and that's not. I feel like you should probably just leave it at 1. There's probably a half medium, so that's an answer. Any more questions?